Hey guys, so this is going to be the general overview for what I name my little turbo pump. It's centrifugal turbo pump project, and it basically encompasses me building an entire turbo pump assembly, centrifugal turbo pump assembly from scratch and testing it and seeing how it validates against a actual detailed paper. So I have these Jupyter notebooks and they document the whole process. So far I just finished up O4 parameter study, so I'm going to go through O1 to O4 to show you what this project is all about. So starting with O1, this is denoted theory and geometry, and we focus on the ideal case here for the maximum possible head in a centrifugal turbopump model. Now, in a centrifugal turbopump, you'll notice that if you do the research, there is many types of losses that can occur, and we'll go into depth with these in the slips and losses notebook. But effectively, these losses can cause substantial decreases in head compared to our optimal case, So this notebook effectively establishes a basis for that ideal head while also establishing our information from the reference paper into a localized location where you can review it and analyze the geometry. So to start, we have our assumptions, and shows everything that applies for our decisions and our equations that we use in this notebook. Past that, we have the constants in the reference geometry table. It's showing the constants that we use. It's effectively defining them. So we have like pump head lift, we have the gravitational constant, we have the speed of the impeller tip, we have the radius of the impeller tip, we have the tangential velocity at the impeller exit, and it gives all the units as well. Now, this is the interesting part, because I found this paper, Miller and Sotis, 1968. It was a detailed performance of a centrifugal pump. It was by NASA. Some guys in 1968 made this paper, and it actually details a entire turbo pump, centrifugal pump assembly, in which they have it actually details a whole centrifugal turbopump assembly in which it details all the geometry so I can really replicate it very easily in SolidWorks. And it also has these graphs, yeah, all the way down here. You can see the detailed graphs that we can use really well to compare to our graphs that we're going to generate with our model in the future. So that's effectively why I selected it. But the one drawback here is that it's radial. So it has radial blades. Conventionally, most impellers are backswept because that's more efficient overall. And so it's a loss of complexity at a cost of high quality data because the other uh, reference pumps I checked, they do not have as good data as this one. So it's just a drawback. And so I have the test conditions listed here. You have the Lewis cold water tunnel, air content ratio, granular content, the test regime, and the configurations. They do say cavitation is present and noted, but they say it's secondary, not really included in the analysis. The impeller geometry, we have all these values. These are values sourced directly from the paper here. There's a geometry section. This is uncertainty. And right up here, this is some geometries. Then this is also some geometries. And this as well. So we can use those geometries, we put them in here. We say the properties, the values, the notes, and all that. And now, from here, Oh, I should mention. So our simplified model, if you notice this impeller here, it has these splitters. There's a better one. Yeah, these splitters right here. We're actually neglecting these splitters. So what we're doing is we're choosing 8 blades by default instead of like what they would have like 21 with the splitters. So that's our only decision, and we're going to see how that affects it in the validation notebook and see what difference that really makes. Now moving on to theory background, we can see that we have the Euler pump equation, which was derived by Euler in about 1756. The Euler pump equation follows from conservation of angular momentum, and with our ideal case where u1 is equal to 0, we have, well, the ideal energy is Cu2U2. And then when we divide both sides of the equation by G naught, then we get the ideal head. And now we get to our actual calculations where we use Python to calculate our ideal head, and we find it's approximately 90 meters. So given this, we can now really see how the difference is across the losses. So see how the losses affect the head, total head. So now going to slip-in losses. It builds on theory and geometry, and it predicts the mathematically predictable losses that we have, like Wisner's shock and friction loss, for our centrifugal impeller. We assume these assumptions. As you can see, we actually lost a good bit of assumptions that used to be here for the 01 theory and geometry notebook. Here's our constants reference in geometry table, so there's the same function as before, and our theory background, which documents how Wisner's slip is developed, how Wisner's slip is quantitatively valued. So you have Cu2 actual, so it's like the slip difference. So when you have a backswept blade, right, or any blade really, but Wisner mainly focuses on backswept. When you have a backswept blade, the water effectively doesn't follow the path correctly. So it doesn't follow the path exactly. It's going to slip a little, inevitably, because it's not directly attached to that blade. So we can say the slip factor is Cu2 actual over Cu2 ideal, where Cu2 is our tangential velocity of our water. Additionally, there's the eddies explanation, where the water has the blades, the back of the blades form a low pressure area, while the front of the blades on the front of the other blade forms a high pressure area. So that effectively creates an eddy, and that eddy causes it to have tangential velocity in the direction of rotation for a backswept blade when it's spinning. So we just need to account for that. We account for that via the slip factor sigma. So here's the history. You can read this once it's out. But the main thing with Wisner's slip is that our impeller actually, by Wisner's predictions, has no effect of slip. So it's perfectly attached by its theory, because when you only have slip when it's backswept like that. From here, we have friction loss as well, and according to one of the papers I read, friction accounts for 40 to 90% of the theoretical head loss, which we'll see if that's true in the future for our model pump. But we can effectively find all these equations that relate for friction. So we have this equation for the head friction, And F is the velocity friction factor, L is the mean stream length through the passage, DH is the hydraulic diameter, and W mean is the average relative velocity. Now, this just describes like how the friction loss function works, the historical basis of it, and all that. Moving on, we have the shock and impingement loss. Now this one's interesting because, so let's say you have a fluid that's just moving forward, right? It's going into an impeller that's spinning. The blades are at a certain angle, right? They're just like deviated at a certain angle. Well, the thing is when that water is going too fast, then it'll hit the blades at like the wrong angle. It won't like slip in nicely with its slight free rotation. It'll instead just hit the blades really hard because it's not naturally going through that angle. Because you have the blade, it's tilted at an angle, and then there's a certain speed in which the fluid rotation, the slight fluid pre-spin that we are not accounting, we actually do account for it later, but we are not accounting for it right now. That occurs when the slight fluid pre-spin causes the velocity vector to be at an angle, and then if that angle is not parallel with the angle of the blade, then it causes what's called incidence loss. So we define incidence loss as the flow rate minus the flow rate at the BEP, the best efficiency point. And so then it's just the difference of the square. Relatively simple. And so we effectively just put all these together, we get the equation, and that's our model head. And this last term is just the Wisner slip factor, so it's just 1 minus the Wisner slip factor times the ideal head. Here's all our code to calculate, and we find that the total loss, the friction loss, is about 3 meters. And so we have about 3% loss total. Darcy's friction coefficient here was about 0.1, which was about reasonable given the other examples that I read where they used Darcy's friction coefficient. W mean, we also use a rough approximation here. So this will be iterated in the next notebook because it's quite a bad assumption, quite a bad approximation, you could say. So there's no slippage. Incidence loss is 0 because we are QBEP. And that's essentially it. Moving on to 03. This is where we actually get graphs. So we have the same assumptions, and we're going to analyze the head versus flow rate, the hydraulic efficiency versus flow rate, and the shaft power versus flow rate. And these will allow us to physically analyze the pump and see how it behaves. So we have a design flow coefficient here at 0.363, which is about 0.148 meters cubed per second. In the following code, we will calculate the parameters, organize them into dependence data from, and plot them. So we have all the variables set up, we create a dictionary, we make the data frames, and we calculate. And then next, we start graphing, and we ultimately get these graphs. So this would be the head versus the flow coefficient. So we can see as the flow coefficient increases, then our head goes down until it hits below 0, which is that's just a limitation of the model. I would have limited it to here optimally. And then we have the flow coefficient versus the hydraulic efficiency. It's essentially the same as the head because you're literally just dividing the head by the ideal head. So it's just normalized. Here you have the frictional head loss versus the flow coefficient. So as the flow coefficient increases, the frictional head loss would also increase, which makes sense, right? If fluid is moving faster, so you get more frictional head loss. And now this one is quite interesting because you have the incidence head loss. So you can see that difference of the squares really coming into application here because you have that difference in flow rate versus the flow rate at BEP. So right when they're equal, you have the minimum incidence head loss, this being 0. And so you should have that as true across the other graphs as well, but you don't. And I said that, I said that this is effectively because the frictional head loss overpowers the incidence head loss. So the way we defined our incidence head loss was at QBEP, it's 0, but that's not going to be true for the friction. The friction is going to be non-zero at QBEP. So this is not going to be our optimal point in this modeled graph, and that's just a limitation that we have to accept. Onto parameter study. We generate a lot of graphs in this one. For this one, we are deviating from the reference pump, and we're analyzing instead the effect of the blade angle, the number of blades, and a bunch of other factors. This one's different because we have to define our angle beta 2 now, because we have it as the blade angle measured from the radial direction, with counterclockwise being positive. So we calculate the effect of the changing blade angle from the radial direction from 0 to 45, though I did change it to 40 just recently because of limitations in the negative head. And so we have that from 0 to 40, and then also changing the blades from 4 to 10. So here we calculate the Wisner slip factor, velocity triangles, losses, and key metrics like head, hydraulic efficiency. And here we define the initial variables. We have results. We set our results initial dictionary. And then we iterate. So we have 4 beta 2 and beta 2 values for z and z values, and it just goes. And so we graph, and then we get this ultimately. So we have parameter sweep study for our model centrifugal pump. You can see the hydraulic efficiency effectively goes down as you increase the number of blades. So that would be due to frictional losses within the pipes. So as you increase, well, it's less pipes, but you get what I mean. As we increase those number of blades, our pipe, or the number of walls that the flow is going to run on increases. And so the hydraulic efficiency would decrease since there's more friction contributing to more loss and thus a lower head in effect. We also have the head. Oh, yeah, I should also mention why it increases with back sweep, decreases with back sweep. So effectively, as it becomes more back sweep, like the slip factor becomes a greater concern as the flow actually starts slipping off. Additionally, the back sweep would increase the incidence loss. Yeah, it would increase the incidence loss because that would change the optimal QBEP. And that relates here because we have the BEP flow coefficient versus back sweep angle, which we did for a linear approximation. So as the back sweep angle increases, the BEP flow coefficient also increases. So that's because as we have more back sweep, we have a higher fluid velocity at the end. So we need more fluid to go through. And here we then have the head and the back sweep angle, and this looks very similar to the hydraulic efficiency. And you can see as back sweep angle increases, head decreases, and as the blade number increases, the head decreases. Going on to the second page, we can now see the loss investigation for the model centrifugal pump. So we have the loss split it into all its components, and we're analyzing how that changes overall. So you have a wiseness slip factor here, and this is versus the back sweep angle. And we can see as we increase that back sweep angle, our wiseness slip factor is going to increase as we noted before. That's what we predicted to happen, and it's shown right here. The wiseness slip factor would decrease. So, as you also increase the number of blades, that wiseness slip factor would actually increase. So that's good, that's less slip. And that's because everything's a lot more compressed, so it's going to follow those veins a lot more closely. Here you have head loss by type for the blade number, and so you have the head loss and the number of blades. So this is a nice bar chart ordered by number of blades, so you can see as this number of blades increases, the incidence stays the same, which is expected. But then the friction decreases as you increase the number of blades. No, that's a slip. What am I saying? Slip decreases as the number of blades increase, and the friction increases as the number of blades increase as well. So then we have the head lost by type for back sweep angle, and we can see that incidence goes way up, all the way up there when the back sweep angle increases. And our friction also goes significantly up. Not that significantly, but it goes slightly up as we increase the back sweep angle. And then our slip also goes slightly up as we increase the back sweep angle. So this is effectively telling you what I just told you. And I also say limitations because all our equations are approximations, so we had to tweak them a little bit to make sure the head didn't do some silly stuff. But yeah, that's effectively it. That's all the notebooks. I will probably tell you about the SolidWorks model in a later video because this one is already 22 minutes long. Thank you for watching.